Hello there, and welcome to Deep Space Sleep. I'm glad you're here. Maybe your day felt busy and heavy with decisions, and now you need a place where everything finally slows. Or maybe you're someone who finds peace in the small details of nature, in knowing that tiny creatures move through the world with quiet precision, that every leaf and blade of grass holds its own gentle secrets, and that intelligence doesn't always announce itself with noise or sighs. Either way, this moment is for you. There's nothing you need to analyze or figure out. Let the world shrink down to something soft and manageable. Let your shoulders ease. Let your breath fall back into a natural rhythm, as if you're sitting in a still meadow at dusk, watching insects drift and wander through warm evening air, each one following patterns older than memory. In this video, we're exploring insect intelligence, not documentaries, not dramatic narrations, but the actual quiet decisions behind tiny lives. The ants that memorize winding paths, the bees that calculate the sun's changing angle, the dragonflies predicting motion midair, the caterpillars feeling the faintest slopes, the hidden minds working inside soil, inside hives, inside the hush of nighttime fields. You'll hear 100 soft facts. Others about the unnoticed creatures who keep forests, grasslands, and entire ecosystems running from beneath the surface. If this helps you rest, you're welcome to subscribe whenever you wake. It helps others find a calm moment too. For now, let the small world move gently around you. Let's begin. Before understanding the deeper forms of insect intelligence, we start with movement. The quiet skill every tiny creature must master to survive. Ants memorizing safe pathways do this through a blend of chemical cues and spatial learning. As they walk, they leave faint pheromone traces that form soft, evaporating lines across soil and leaf litter. With each trip, they refine the route, adjusting around stones, roots, and shifting shadows. The more reliable the path, the stronger the chemical trail becomes, almost like the quiet outline of a well-worn footstep in sand. Individual ants also use subtle visual landmarks: a tall blade of grass, a patch of darker soil, the curve of a twig. These tiny markers build a mental map no larger than a thumbnail, but detailed enough to guide them home. And as these trails strengthen, bees begin their own form of gentle navigation, tracing the shifting angles of sunlight. Bees tracing soft sun angles navigate with a grace that feels almost fluid. Inside their tiny brains lies an internal clock that helps them compensate for the sun's movement across the sky, letting them fly straight toward flowers even as the light slowly shifts. They read polarized light patterns, faint, invisible grids scattered across the sky to orient themselves even on hazy days. As they travel, their wings create small vibrations that echo against petals and leaves, helping them judge distance by the way air flows along their bodies. Flowers bloom in patches of color. Bees see far more vividly than we do, glowing with ultraviolet patterns that point them toward nectar. When they return, they convert all this quiet information into a dance, sharing directions with the colony, using angles, steps, and soft vibrations. And while bees follow sunlight, butterflies begin drifting into rising columns of warm air. Butterflies following thermal winds rise gently through columns of sunlight-warmed air called thermals. These warm updrafts lift their lightweight wings with almost no effort, allowing them to glide long distances while conserving energy. Their wings are covered in microscopic scales that sense small changes in airflow, helping them adjust angle and position with subtle, almost invisible motions. As they move, they scan the landscape below patches of color, shapes of leaves, and the faint shimmer of moisture. Some species migrate across continents using these soft currents, repeating pathways older than human memory. They read the temperature of air pockets, the direction of breezes, and even the slight tug of Earth's rotation through atmospheric flow. Floating from one warm column to the next, they seem to follow an unseen map traced in rising heat. And as the day settles into evening, beetles begin steering through soft moonlight. Beetles steering by moonlight use the sky like a quiet compass. Many species can detect polarized lunar light. The faint, ordered pattern created as moonlight scatters through the atmosphere. This pattern helps them hold straight lines across open ground, especially in desert environments where landmarks are scarce. Some species even use the Milky Way as a guide, aligning their movement with the bright band of stars stretching above. Their eyes contain specialized photoreceptors tuned to low light, amplifying small glints on sand and leaves without overwhelming their vision. While walking, beetles sense texture changes through the tiny hairs on their legs, adjusting steps around obstacles with soft precision. Even their antennae help them feel the direction of night breezes. Under this calm navigation, the world sounds quieter, shadows feel thicker, and the cool air carries fewer scents. And deeper still, moths begin sensing the faint magnetic fields that guide their nighttime journeys. Moths sensing faint magnetic fields rely on specialized proteins that react to Earth's geomagnetic lines, giving them an internal compass hidden beneath soft wings. These proteins, likely cryptochromes, shift chemically in response to magnetic direction, allowing moths to orient even in complete darkness. Their navigation blends magnetic cues with the scent of flowers, the temperature of air layers, and the glow of distant horizons. As they fly, their large antennae sweep gently through the air, sampling faint odors that help them stay on course. The night around them is full of gradients, slight changes in moisture, warmth, and wind, and moths read these like quiet landmarks. They adjust their wing beats to glide whenever possible, saving energy for long migratory flights. Their movements seem effortless, drifting through moonlit spaces with a calm that feels almost dreamlike. And with this soft mastery of Earth's invisible signals, the next forms of insect intelligence begin to unfold. Dragonflies planning gentle flight paths glide with a precision that looks effortless but comes from remarkable sensory processing. Their compound eyes capture nearly 360 degrees of vision, detecting even the slightest motion in the air. Tiny shifts in wind pressure register along their wings, allowing them to adjust course before turbulence reaches them. In calm air, they trace smooth arcs, choosing flight lines that minimize energy use while maximizing stability. Their nervous systems make predictions milliseconds ahead, letting them meet moving targets or drift past obstacles with soft, exact movements. On quiet ponds, their reflections skim across the water's surface like slow-moving threads. When sunlight fades and colors soften, dragonflies choose lower, more sheltered routes, following the cool, still pockets that form near reeds. And deeper underground, other insects navigate without light at all, like termites, who orient flawlessly inside complete darkness. Termites orienting inside darkness move through their intricate tunnels using senses far more delicate than sight. Their antennae sweep forward in soft arcs, reading chemical gradients left by other colony members. Every wall and curve carries information: density, temperature, humidity, all of which help termites maintain direction in pitch-black silence. They also feel minute vibrations that travel through soil, letting them sense approaching dangers or distant activity within the colony. Their internal maps are built from repeated movement. After enough trips, the patterns of each tunnel become familiar, like a memory stored in the body rather than the mind. Inside these dim corridors, air stays cool and still, shaped by the architecture termites construct grain by grain. And when they pause, the world grows so quiet that even a subtle wing flutter can be felt. Outside these tunnels, crickets are mapping nighttime soundscapes with equal subtlety. Crickets mapping night soundscapes rely on vibrations and faint acoustic cues carried through grass, soil, and cool evening air. Their ears, located on their legs, detect tiny shifts in frequency, allowing them to interpret direction based on the timing of each sound wave. Every cricket call becomes a landmark, a soft beacon that outlines safe areas and reveals where rivals or mates might be hiding. As they move, they feel how sound changes around rocks, roots, and blades of grass, using those distortions much like visual creatures use shadows. The night around them is full of gradients, temperature dropping in low dips, moisture rising near ponds, wind settling in sheltered hollows. Crickets read these patterns instinctively, finding paths that keep them hidden and comfortable. And while they map the world through sound, caterpillars navigate by touch alone, adjusting quietly to the subtle slopes beneath them. Caterpillars adjusting to subtle slopes explore their world at a pace where every millimeter matters. Their many tiny legs grip surfaces with soft precision, sensing texture, moisture, and angle all at once. When the ground tilts, even slightly, pressure shifts along their flexible bodies, prompting them to lean and redistribute weight to maintain balance. Their simple nervous systems convert these gentle cues into slow, deliberate movements that keep them safe from sudden falls or unstable leaves. As they climb, they test each surface with rhythmic taps, reading whether it bends too easily or holds firm. Dew on leaves cools their skin and changes the friction beneath their feet, guiding them toward warmer, drier roots. And when they rest, curled in small arcs, the world seems to pause with them. As they follow slopes in the quiet dark, fireflies above drift toward faint glowing signals. Fireflies drifting toward quiet signals navigate summer nights using soft pulses of bioluminescent light. Each glow is produced by a chemical reaction within their lantern organs, controlled with precise timing to create patterns unique to each species. These silent flashes work like gentle messages across open air, guiding fireflies toward one another in slow, floating arcs. Their eyes are specially adapted to detect faint light, allowing them to interpret distance and direction even under moonless skies. Humidity, temperature, and wind all influence how their signals travel, and fireflies adjust altitude or timing to keep their communication clear. Moving through warm air, their bodies leave slight trails of shifting brightness, like tiny comets drifting through grasslands. Every flash becomes both a beacon and a path, and as they settle into the rhythm of their glowing exchanges, the deeper intelligence of insect life begins to reveal itself. Once their movement is shaped, the mind behind it reveals itself small, precise, and surprisingly wise. Neural pathways, forming tiny decision loops, operate inside insect bodies with remarkable efficiency. Their brains contain only thousands to millions of neurons, yet each neuron specializes in rapid, purposeful processing. Signals move along these pathways in patterns shaped by experience. A remembered scent, a successful turn, a safe patch of shade. Even simple circuits can switch between exploration and caution, adjusting behavior based on the environment's subtle cues. These loops help insects choose when to move, when to pause, and when to shift direction by fractions of an inch. What looks instinctive often includes quiet learning, built from repeated successes stored in microscopic networks. As these neural loops shape small choices, their senses step forward to refine what they perceive, beginning with compound eyes, filtering gentle patterns of light and color. Compound eyes, filtering gentle patterns, allow insects to see the world as a mosaic of shifting shapes and soft cues. Each eye is made of hundreds or thousands of tiny lenses, called ommatidia, which capture narrow slices of light. Instead of forming a single image, insects integrate these fragments into a broad, low-detail picture that highlights motion and contrast. This gives them a sense of the world that feels more like movement than form, shadows sliding across leaves, brightness rising along a horizon, the flicker of a passing wing. Some species can detect ultraviolet markings invisible to humans, reading them like glowing signs on petals or stems. The calm precision of this vision keeps them safely oriented as they move, and while their eyes sense distant changes, their antennae gather nearby chemical signals with equal subtlety. Antennae gathering quiet chemical signals function like gently moving laboratories, constantly sampling the air for traces of scent, moisture, and temperature. Each antenna is lined with microscopic receptors tuned to specific molecules, pheromones, plant volatiles, or even faint compounds released by predators. As insects move, the slight rhythm of their antennae increases the flow of air across these receptors, helping them distinguish old scents from new ones. Chemical gradients become soft pathways. Stronger concentrations suggest direction. Weaker ones fade like distant memories. Antennae also help insects sense humidity, guiding them toward environments that protect their delicate bodies from drying out. Combined with their eyes, these chemical senses create a layered map of the world around them. And as these signals accumulate, the insect's microbrain begins mapping small landscapes with quiet intention. Microbrains mapping small landscapes rely on a blend of sensory memory, repeated movement, and subtle pattern recognition. Even with only a fraction of the neurons found in larger animals, insects build internal maps that help them navigate efficiently. They remember the angle of light on a familiar route, the scent of a safe hiding place, and the feel of stable ground underfoot. Each experience adds detail to a spatial memory shaped more by motion than distance. Their brains create simplified versions of the world. A curved leaf becomes a landmark, a warm stone a boundary, a cluster of stems a corridor. These maps help them choose efficient paths, avoid hazards, and return to food sources with surprising accuracy. Beneath all this, sensory hairs on their bodies translate faint vibrations into signals that refine every step. Sensory hairs translating faint vibrations act like tiny motion detectors distributed across an insect's body. These hairs, known as mechanoreceptors, bend in response to even the slightest disturbances, airflow from a passing wing, a predator's footstep, or the tremble of a leaf shifting under weight. When a hair bends, it triggers a nerve impulse that tells the insect not just that something moved, but how fast and in what direction. These signals integrate seamlessly with visual and chemical cues, giving insects a multi-layered perception of their environment. In calm surroundings, vibration sensing becomes a form of early warning, allowing insects to react before danger is visible. In peaceful fields or quiet soil chambers, these hairs help them coordinate stillness or motion with precise timing. And as vibration becomes understanding, the next layers of insect intelligence begin to unfold. Thermal cues shaping insect choices create an invisible temperature map that guides nearly every movement they make. Insects are ectothermic, meaning their bodies depend on external warmth to function, so they constantly measure tiny shifts in heat around them. Sensitive receptors on their legs, antennae, and even wing edges detect differences of just a fraction of a degree. Warm patches signal efficient movement, safe feeding spots, or sheltered places to rest, while cooler areas warn of energy loss or predators lurking in shade. Many species follow rising warmth in the morning to activate their muscles and retreat into cooler refuges during the hottest hours. This continuous conversation with temperature shapes their day with a gentle rhythm, and as insects follow these quiet thermal signals, they also read the changing gradients of light that stretch across their paths. Light gradients guiding peaceful navigation help insects orient in a world where brightness constantly shifts. Instead of interpreting scenes in sharp detail, many insects rely on light intensity and direction, following the soft slope between bright and dim areas. Their eyes detect subtle changes in polarization from the sky, allowing them to navigate even when clouds diffuse the sun. This gradient-based vision lets them choose paths that avoid glare, reduce exposure to predators, and lead toward resources like flowers or shaded resting sites. At dawn and dusk, when shadows grow long and colors cool, insects use the angle of light to maintain direction with surprising consistency. These gradients act like gentle rails beneath their flight or footsteps. And while light helps them move across the open world, moisture shifts trigger even softer responses within the environments they explore. Moisture changes, triggering soft responses, influence insect behavior at nearly every stage of life. Their bodies lose water quickly, so even the faintest shift in humidity signals comfort, danger, or opportunity. Hygroreceptors, specialized cells on their antennae and mouthparts, sense moisture levels in the air and on surfaces. A slightly damp leaf might lead a beetle toward shelter. A dry breeze may send an ant deeper underground. For some species, humidity determines when eggs hatch or when larvae seek new food sources. In warm evenings, rising moisture creates ideal conditions for flight, communication, or feeding. These subtle cues form quiet pathways insects follow without hesitation, adjusting their direction the way we adjust to a change in wind. And as moisture guides them through their habitats, internal circadian rhythms rise to meet the gentle pulse of daylight. Circadian rhythms, syncing with sunlight, allow insects to shape their lives around predictable cycles of day and night. Within their tiny bodies, a cluster of clock genes produces chemical patterns that oscillate over roughly 24 hours. These internal rhythms synchronize with environmental signals. The first warmth of sunrise, the soft cooling at dusk, and the gradual dimming of light through clouds. Many insects feed, rest, or migrate at specific points in this cycle, conserving energy by acting when conditions are most favorable. Bees, for example, align their daily routines with the blooming schedule of flowers. Nocturnal species awaken precisely when light levels fall below safe thresholds. These rhythms create a steady, calming structure in their lives. And beneath these natural clocks, simple neurons begin solving quiet puzzles that help them survive. Simple neurons solving hidden puzzles work together in networks far smaller than those of larger animals. Yet they perform astonishing tasks. With only a few interconnected cells, insects can recognize patterns, learn safe routes, and choose between competing stimuli. These neurons encode past successes like finding food or avoiding danger and compare them to present conditions. When an insect encounters something unfamiliar, its neural circuits activate tiny decision trees, weighing options in milliseconds. This fast, efficient processing feels almost reflective, even though it relies on compact circuitry. Some species can even generalize from experience, adjusting behavior when circumstances change. Their tiny brains solve navigation, memory, and communication challenges with elegant simplicity. And as these quiet neural puzzles unfold, the broader intelligence of insect life continues to reveal itself. With perception comes communication messages, carried in scents, vibrations, and delicate movements. Chemical trails guiding wandering ants form some of the most elegant information systems in nature. As ants walk, they lay down faint lines of pheromones that evaporate slowly into the air. Another ant crossing the same ground senses the trail with its antennae, interpreting concentration gradients as directional cues. Stronger scent means the path was used recently. Weaker scent signals an older or less reliable route. These trails help entire colonies find food, avoid danger, and return to their nest with quiet precision. When the environment shifts a new obstacle, a fallen leaf, a sudden wind, ants update their trails instantly, reinforcing useful paths and letting old ones fade. This chemical language is silent but dynamic, and as the trails guide movement across the ground, gentle wing vibrations begin shaping messages above it. Gentle wing vibrations, sharing messages, create a form of communication that feels almost musical. Many insects, especially bees and certain wasps, use subtle vibrations to relay information about food, danger, or direction. These vibrations travel through air, leaves, or the walls of a hive, carrying meaning without needing sound. A bee returning from a successful flight might tremble softly to signal the richness of a nectar source, while another increases the vibration pattern to warn others of a threat nearby. The frequency and duration of these vibrations form a quiet vocabulary understood instinctively by the colony. Even tiny shifts, slower or faster pulses, change the message. The stillness of a hive makes these signals clearer, allowing insects to listen with their legs and antennae. And as vibrations ripple through the colony, pheromone clouds begin drifting through grass, extending communication into open air. Pheromone clouds drifting through grass act like invisible messages floating between blades and stems. When released, these chemical signals spread outward in soft, expanding plumes shaped by temperature, humidity, and wind. Some pheromones warn of nearby predators. Others guide mates across long distances. Ants, beetles, moths, and even some flies rely on these drifting scents to maintain connection with their group or locate specific individuals. As an insect moves through the environment, it reads the intensity and direction of each chemical trace, following gradients the way we follow distant lights. These clouds can linger for minutes or dissipate instantly depending on weather conditions. At sunset, when air cools and settles, pheromones travel more smoothly, creating calm pathways of scent. And as these chemical messages float through twilight meadows, tactile cues begin shaping the close-knit world inside hives and nests. Tactile cues shaping hive behavior create a language of touch that thrives in dark, crowded spaces. Bees and other social insects rely heavily on physical contact to coordinate tasks when vision is limited. A brush of antennae may signal recognition. A gentle push indicates a shift in duty. A soft tap on the abdomen can guide a worker towards stored food. These tactile patterns travel rapidly through colonies, forming networks of communication that mirror the structure of the hive itself. Even temperature changes, a warm cluster or a cool outer layer carry meaning, influencing where individuals move and how they care for larvae. In darkness, touch becomes both map and message, allowing insects to navigate with certainty. And just beyond these crowded chambers, moths exchanging scent in starlight add another layer of quiet, delicate communication. Moths exchanging scent in starlight use the night sky as the backdrop for one of nature's most subtle communication systems. Many species release pheromones that drift upward in narrow streams, detectable over extraordinary distances. Males follow these invisible ribbons by continuously sampling the air with their feather-like antennae, adjusting direction as the scent intensifies or weakens. Starlight and cool nocturnal temperatures help stabilize these chemical trails, allowing them to travel farther without dispersing. As moths glide through darkness, their wing beats push small eddies of air that reveal where the scent sharpens, helping them trace the plume's source with quiet accuracy. When two individuals finally meet, their communication becomes even softer, gentle wing touches, faint vibrations, and delicate chemical exchanges. And with this nighttime dialogue, the stage is set for the next forms of quiet problem-solving to unfold. Bees using calming body language rely on subtle movements to communicate without sound. Inside a hive, where thousands of individuals crowd together in warm darkness, visual cues are limited, so bees use small shifts of posture to guide one another. A gentle lowering of the abdomen can indicate reassurance, while a slow, relaxed walk signals that food sources are stable and nearby. Workers often touch antennae lightly to confirm identity, reinforcing trust within the colony. Even the speed at which a bee moves conveys meaning. Calm, measured steps spread a sense of safety, while fast, erratic motions alert others to danger. These body cues help maintain harmony in a space that could otherwise feel chaotic. And beyond these clustered halls of wax and honey, termites begin tapping faint rhythms that echo through their hidden tunnels. Termites, tapping faint rhythms, use vibrations as a precise communication tool within their underground world. Living in darkness, they rely less on scent or sight and more on the subtle tremors that move through soil and wood. When a termite detects danger, it taps its head or abdomen against the tunnel surface, sending rhythmic pulses that spread quickly through the colony. These signals can warn others to retreat, call workers to reinforce walls, or coordinate tasks during construction. Even slight differences in tempo and intensity carry distinct meanings. The vibrations travel far in the quiet soil, like soft drumbeats beneath the earth. As these pulses fade, other insects above ground carry their own subtle signals, grasshoppers broadcasting low, soft calls into the evening air. Grasshoppers broadcasting low, soft calls shape the soundscape of warm nights. Their songs, produced by rubbing specialized structures on their wings or legs, serve purposes beyond attracting mates. The tone, pitch, and rhythm of these calls carry information about territory, temperature, and environmental conditions. Grasshoppers adjust their songs depending on humidity, wind, and even moonlight levels, creating patterns that other insects can interpret from a distance. These calls are quieter and more measured than the louder chirps of crickets, blending into the background like a soft vibration traveling across tall grass. As night deepens, the calls become part of the landscape's gentle hum. And while grasshoppers use sound, paper wasps rely on something more unusual, recognizing subtle faces within their own colonies. Paper wasps, recognizing subtle faces, demonstrate one of the most surprising forms of insect intelligence. Unlike most insects, which rely heavily on scent and general patterns, paper wasps can distinguish individual colony members by their facial markings. Their brains contain specialized regions that process shape and contrast, allowing them to remember unique patterns on the faces of their nestmates. This recognition helps maintain social order, reducing conflict and strengthening cooperation. Wasps use brief visual glances combined with antennal touches to confirm identity, building a quiet social memory within the nest. These small recognitions guide how they divide tasks, defend territory, and share resources. And in the broader insect world, many species convey reassurance in simpler ways through gentle signals that quietly say safe. Insects saying safe with gentle signals do so through a subtle blend of scent, posture, vibration, and movement. These cues tell nearby individuals that food is ample, shelter is stable, and the environment holds no immediate threats. Ants soften their antennae movements when conditions are calm. Bees lower their wing beats. Some beetles release faint chemicals that signal peace. Even the tempo of walking can communicate security. When many individuals display these relaxed signals at once, a collective calm spreads through the group, allowing colonies to focus on feeding, tending young, or resting. These soft markers of safety keep insect societies balanced and efficient, and as the air fills with these quiet reassurances, the stage shifts toward deeper problem-solving in the hidden world of insect intelligence. Communication turns to strategy, small decisions forming patterns of quiet problem-solving. Bees remembering hidden flower spots rely on a blend of visual memory, scent cues, and internal timing to locate blooms that are not always visible from afar. Their eyes capture patterns of color, shape, and polarization, storing these details in neural circuits that allow them to return hours or even days later. A bee may visit dozens of flowers, yet recall which ones refill nectar fastest, which petals hold warmth, and which colors promise richer rewards. They navigate back to these secret patches, using the sun's position and faint landscape features like shadows or tree outlines. Even when wind alters the environment, bees adjust their approach smoothly, refining the route with each journey. And as they memorize these small rewards, ants nearby begin solving maze-like paths with equal quiet precision. Ants solving maze-like paths demonstrate a surprising degree of spatial reasoning despite their tiny brains. When exploring complex routes, ants combine chemical trails with visual cues and proprioception, the sense of their own movement, to map twists and turns. They constantly test multiple branches, marking each option with pheromones that strengthen or fade depending on success. Over time, their colony collectively discovers the most efficient route, reinforcing it through repeated travel while abandoning dead ends. Individual ants update their choices based on the freshest scent or the softest gradient of light along the tunnel. Even in artificial mazes created by researchers, ants systematically reduce errors until they move almost directly from start to finish. As these quiet navigators refine their paths, cockroaches nearby are choosing the safest shelters in ways that also reveal quiet problem-solving. Cockroaches choosing safest shelters do so by evaluating darkness, temperature, and humidity with remarkable sensitivity. When presented with multiple hiding places, They prefer those that maintain stable warmth and offer deep shadows, reducing their chances of being detected by predators. Their antennae sample air currents for moisture and scent, while tiny mechanoreceptors along their legs sense the texture and firmness of surfaces. Cockroaches also exhibit collective decision-making. When many individuals cluster in one shelter, others follow, interpreting the presence of companions as evidence of safety. Experiments show they weigh trade-offs, choosing slightly brighter spaces if they hold better humidity, or tighter spaces if they feel more secure. Their choices unfold slowly, with deliberate pauses that resemble contemplation. And as they settle into their chosen refuge, wasps begin recognizing safe routes with equal subtlety. Wasps recognizing safe routes rely on a combination of visual memories, chemical markers, and careful scanning of their surroundings. While navigating between nest and food sources, they memorize specific landmarks such as tree shapes, rock patterns, and light angles. Their flight paths often include slow hover pauses where they turn in small arcs, capturing a panoramic imprint of the area. Some species even perform orientation flights, gentle spirals taken when leaving a new nest to build a mental map before venturing farther. Wasps avoid unstable air currents and bright predator-exposed areas, selecting routes that offer shade, steady airflow, and predictable cues. When they return, they adjust micro-movements of their wings to land precisely on narrow ledges or delicate paper nests. As these careful navigators settle, crickets nearby repeat successful choices using their own quiet learning system. Crickets repeating successful choices use memory shaped by simple reinforcement. When a particular hiding spot provides warmth, silence, or safety, they store the experience in short-term neural circuits that influence future decisions. Experiments show that crickets will return to locations where they previously found favorable conditions, even when those spots lack obvious scent markers. Their antennae confirm textures and scents along the route, while their sensitive legs detect subtle temperature zones in soil or grass. Over time, successful hiding spots become preferred zones that crickets approach without hesitation. If conditions change cooler air, shifting vegetation, they adapt, testing alternatives until a new safe area is found. This repetition creates a quiet behavioral rhythm, a soft pattern of learned choices guiding them through the night. And with these gentle decisions, the deeper layers of insect problem-solving continue to unfold. Dragonflies predicting motion rely on a sophisticated neural system that allows them to anticipate where their prey or a moving object will be in the near future. Their brains contain specialized target-detecting neurons that calculate velocity, direction, and acceleration almost instantly. Instead of reacting to where something is, dragonflies adjust course toward where it will be, making their flight appear effortless and fluid. They track movement even against cluttered backgrounds, filtering out irrelevant details with remarkable precision. Their wings rotate independently, creating micro-corrections that stabilize their trajectory in wind or shifting air. This predictive ability gives dragonflies a near-perfect success rate during hunting, but it also shapes how they navigate peacefully through reeds and still water. As they glide through the air with quiet confidence, beetles below are selecting optimal hiding places with their own gentle reasoning. Beetles selecting optimal hiding places evaluate their surroundings with a mix of thermal awareness, scent detection, and tactile exploration. Many species prefer stable microclimates, choosing spaces where temperature stays even and light cannot penetrate deeply. Their antennae sweep across surfaces, sampling humidity and chemical traces left by other insects or plants. They test cavities with their legs, feeling for textures that promise safety, rough bark for grip, soft soil for cover, or hollow stems for silence. Some beetles hide under stones that retain the day's warmth, while others slip beneath decaying leaves that stay moist and cool. The decision is rarely random. Beetles often explore several options, returning to the one that offers the calmest, most sheltered environment. And while beetles quietly settle into their chosen refuge, Butterflies above search the landscape for calm landing zones shaped by softness and light. Butterflies choosing calm landing zones rely on a careful combination of visual cues, airflow sensing, and surface chemistry. Their delicate legs contain chemoreceptors that taste a leaf's suitability the moment they touch down, letting them judge if it can hold their weight or nourish their larvae. Before landing, butterflies hover briefly, reading wind eddies that swirl around plants and scanning for colors that blend gently with the environment. They avoid harsh reflections and unstable leaves, favoring spots warmed by soft sunlight and sheltered from sudden gusts. Once landed, they remain extremely still, absorbing warmth through their wings and letting surrounding patterns of shadow calm their movements. This peaceful settling mirrors another insect's quiet strategy: antlion larvae engineering traps beneath loose sand with exquisite precision. Antlion larvae engineering quiet traps construct funnel-shaped pits that function as simple but effective physics-driven snares. The larvae burrow backward, flinging grains of sand in steady spirals as they carve a smooth, unstable slope. Each grain is deliberately placed. Too coarse, and the pit loses flow. Too fine, and it collapses. The angle is tuned to just below the point where sand naturally avalanches, ensuring that any small insect entering the pit slides downward toward the center. When prey stirs the sand, the antlion senses vibrations through the substrate and flicks more grains upward to destabilize the slope further. This engineering requires no planning in the human sense, yet arises from instinctive knowledge shaped over millions of years. And as these tiny architects rest beneath the sand, termites nearby are busy building balanced structures above ground. Termites building balanced structures create mounds that act as living ventilation systems, regulating temperature, humidity, and airflow with astonishing precision. Their constructions use a combination of soil particles, saliva, and plant fibers arranged in layers that allow heat to escape while drawing fresh air inward. Termites constantly adjust tunnel sizes, wall thickness, and chamber positions based on subtle environmental feedback. When carbon dioxide rises in one area, workers open a passage. When humidity drops, they seal another. Their movements are coordinated through pheromones and vibrations, resulting in structures that stay stable despite wind, rain, and shifting ground. Each mound is shaped not by a single blueprint, but by thousands of tiny corrections made moment by moment. And with these balanced forms rising quietly from the earth, the intelligence of insect societies becomes even more evident. And when many small minds act as one, intelligence becomes a flowing, collective calm. Ant colonies dividing tasks softly do so without a leader, relying instead on simple cues that scale into complex coordination. Each ant senses local conditions, food availability, brood temperature, pheromone density, and adjusts its role accordingly. Workers may forage in the morning, tend larvae in the afternoon, and repair tunnels at dusk, shifting roles with a gentleness that feels almost choreographed. This flexibility emerges from positive feedback loops. When more individuals perform a task, the associated chemical signals strengthen, subtly inviting others to join. When a job nears completion, the signals fade, prompting ants to disperse toward new needs. The colony becomes a single flowing mind made of thousands of tiny decisions. As ants rearrange their work in this soft rhythm, bees nearby begin distributing labor by need with equal grace. Bees distributing work by need rely on constant sensory monitoring inside the hive. Temperature, brood age, nectar stores, and even vibration patterns inform how many bees shift toward each task. When the brood nest cools slightly, workers cluster around it. When nectar flows increase, foragers surge outward in larger numbers. No signal is shouted. Everything moves quietly through pheromones and subtle wing vibrations. A young bee may begin as a cleaner, then gradually transition to nursing, comb building, guarding, and finally foraging as her physiology changes. This age-based progression blends with moment-to-moment adjustments determined by the hive's needs. If nectar suddenly floods in, older bees may revert to in-hive tasks while younger ones venture out. These fluid exchanges keep the colony balanced. And beyond the hive walls, termites organize construction teams with an equally soft but astonishing coherence. Termites organizing construction teams build in coordinated waves without any central commander. Each worker responds to simple environmental cues: fresh soil pellets, temperature shifts, carbon dioxide levels, and these cues cascade into collective structure building. When a termite places a grain of soil, the shape and chemical signature of that pellet subtly encourage nearby workers to add their own. This creates pillars, arches, and walls that grow organically, guided entirely by local interactions. Workers specialize based on age and physical condition. Younger termites gather moist soil, while older ones shape and compact it. If a tunnel grows too warm, a cluster of workers widens it. If airflow becomes unstable, they adjust internal vents. These small, synchronized actions create towering mounds that regulate climate with extraordinary precision. As termites sculpt their living architecture, locusts above ground demonstrate their own form of collective calm by coordinating movement across open landscapes. Locusts coordinating calm movement are often imagined as chaotic swarms, yet their group behavior is surprisingly ordered at its earliest stages. When conditions are stable and food abundant, locusts move in loose, peaceful formations guided by visual cues and the soft pressure waves of bodies moving nearby. Each individual aligns its direction with neighbors while maintaining a comfortable spacing shaped by air currents and leg touch signals. Their brains contain simple algorithms that convert personal movement into group flow. If those around slow, they slow. If those ahead drift left, they follow. This creates shifting ribbons of insects that glide over ground without collisions. Only when environments change drastically do these groups intensify towards swarming. In their calmer state, locusts behave more like drifting particles than destructive forces. And as they move quietly across grasslands, wasps nearby practice their own cooperation by sharing food gently among nestmates. Wasps sharing food quietly rely on mutual exchange called trophallaxis, in which individuals pass liquid nourishment mouth to mouth. This soft flow of food carries more than calories. It also spreads chemical information that helps regulate colony behavior. Workers returning from foraging offer droplets to nestmates, who interpret the scent and warmth of the food as clues about environmental conditions. If nectar sources are rich, sharing becomes more frequent and encourages other wasps to forage. If food is scarce, exchanges grow slower, prompting workers to conserve energy. This gentle trade also strengthens social bonds within the colony, reducing conflict and reinforcing hierarchy through calm, predictable interactions. Even larvae contribute by releasing faint chemical signals that indicate hunger level, guiding adults to feed them in balanced cycles. And as wasps complete these quiet exchanges, the deeper networks of insect cooperation continue unfolding into the next layers of swarm intelligence. Aphids, adjusting to group signals, respond to subtle chemical cues released by their companions. When predators approach, alarm pheromones drift through the air in faint, peppery traces, prompting the group to tighten its formation or move to the underside of leaves, where humidity is higher and danger is lower. During peaceful conditions, aphids release softer signals that encourage feeding and slow, coordinated movement across stems. Each individual senses not only the chemicals, but also the density and temperature shifts created by group clustering, using these quiet cues to decide whether to settle, wander, or reproduce. Their collective presence influences plant chemistry too. As they feed together, plants release defensive compounds that change leaf taste, guiding aphids to more suitable spots. And as these tiny groups adjust to one another in silence, fire ants nearby prepare to form floating rafts in a different display of cooperative intelligence. Fire ants, forming floating rafts, rely on their ability to cling to one another using claws, mandibles, and the hydrophobic texture of their exoskeletons. When rising water threatens their colony, thousands gather, linking bodies into a buoyant structure that resists sinking even under constant motion. Each ant shifts position slightly, distributing weight and adjusting to water currents, creating a living raft that can float for days. Air trapped between their bodies forms tiny pockets that increase buoyancy, while worker ants move larvae and the queen toward the drier, central regions. Individuals rotate periodically between submerged and exposed positions to avoid fatigue or drowning. The raft flows as a single unit, bending gently around obstacles as if guided by intention. And as this living platform drifts with the current, honeybees elsewhere are making their own collective decisions, choosing new homes through a quiet form of democracy. Honeybees, democratically choosing new homes, use a surprisingly fair system rooted in exploration and consensus. When a colony becomes too crowded, scout bees venture out to evaluate potential nest sites, inspecting each location for size, warmth, safety, and available resources. Upon returning, scouts perform waggle dances that encode the distance and direction of the site they favor. The strength and duration of the dance reflect the scout's confidence, subtly persuading others to investigate. Over time, more bees visit the best sites, and their dances grow more frequent, creating a gentle competition of ideas. Once a threshold of agreement is reached, the entire colony lifts into the air and moves as one. This collective decision-making balances speed with accuracy, ensuring survival through cooperation rather than force. And after bees reach consensus, swarms in other species show their own flowing logic as they move in coordinated patterns. Swarms following flow-like patterns behave less like individual insects and more like a single, fluid organism. Each insect responds to three basic cues: stay close to neighbors, avoid collisions, and align movement with the group. These simple rules create large-scale patterns that ripple across landscapes like waves of air or drifting clouds of dust. Swarms shift shape depending on wind, terrain, and light, opening and tightening just as water adjusts around rocks. Individuals at the edges feel pressure from the group and adjust speed to maintain cohesion, while those at the center move with minimal effort, carried by the collective flow. This emergent behavior requires no leader. Coordination arises automatically from tiny, repeated decisions. And as these patterns stabilize, the colony develops something deeper: group memories that shape long-term behavior. Group memories shaping colony behavior form through repeated interactions, shared cues, and accumulated environmental experiences. Insects learn collectively which paths lead to food, which shelters stay dry, and which threats recur season after season. These memories are encoded not in a single brain but across the colony's distributed network of individuals. Chemical trails linger, hive vibrations change, construction patterns shift, and young insects inherit tendencies shaped by the group's past. When conditions change, colonies draw on these collective traces to adapt faster than any single insect could. Over years, these memories influence everything from migration timing to nest architecture to foraging strategies. And as these quiet, shared experiences deepen, the intelligence of the colony becomes more than the sum of its tiny parts. Behind every movement lies memory, small but persistent, shaping insect lives. Bees remembering colors for days use a sophisticated form of associative learning tied to nectar rewards. When a bee discovers a flower with abundant food, its brain strengthens neural pathways that link the color of the petals to the sweetness it found. This memory persists even after multiple foraging trips, allowing bees to return directly to profitable patches without hesitation. Their color vision extends into ultraviolet, revealing patterns invisible to humans: soft rings, glowing veins, or bright directional cues. When light shifts with time of day, bees still recognize these hues, adjusting their flight gently to account for the sun's angle. Even in changing weather, bees recall which shades once held promise, helping them conserve energy. And as bees store these vibrant impressions, ants in nearby soil begin imprinting on safe roots with their own quiet precision. Ants imprinting on safe roots create internal maps shaped by repeated movement and faint chemical cues. When an ant discovers a stable, obstacle-free path, its steps reinforce pheromone signals that subtly mark the ground. Other ants follow, adding their own traces until the trail becomes a trusted corridor. Over time, individuals memorize landmarks, textures of soil, the slope of a route, or the shadow cast by a particular stone. These cues merge with the chemical signs to create a hybrid memory stored in both environment and body. If the path becomes blocked, ants explore calmly, branching outward until they rediscover a workable route and imprint it anew. This flexible mapping system lets colonies adapt to shifting conditions with surprising speed. And while ants follow these familiar pathways, moths nearby are adjusting to new scents carried on the evening air. Moths adjusting to new scents rely on antennal receptors capable of detecting individual molecules in low concentrations. Their olfactory system is both sensitive and adaptable when a new scent appears, such as a flower blooming out of season or a different pheromone drifting on warm wind. Their neural circuits reorganize to prioritize this signal. Moths blend scent with temperature gradients and airflow changes, tracing the source with slow, deliberate adjustments. Over repeated encounters, their brain strengthens the pathways associated with the new odor, allowing them to follow it more efficiently. This learning helps them locate food, mates, and safe resting places in landscapes that shift nightly. Their movement becomes a drifting dance shaped by invisible trails. And as moths refine their sense of smell, beetles near the forest floor begin learning from gentle cues in their own quiet environments. Beetles learning from gentle cues rely on simple conditioning that builds through repeated experiences. When beetles encounter a surface that provides warmth, moisture, or food, they store the sensation within short-term neural circuits. Over time, these experiences influence their choices, guiding them back to areas that previously offered comfort. Their antennae gather subtle information: the faint scent of decaying wood, the coolness beneath a stone, the humidity around moss. Each cue becomes part of a soft internal record. If conditions change, beetles test alternatives and update their preferences, demonstrating a quiet adaptability. They learn which hiding spots remain stable through weather shifts and which pathways lead to safer feeding grounds. These small lessons accumulate like threads woven into daily movement, and as beetles refine their choices, flies above them begin improving with repetition through their own compact intelligence. Flies improving with repetition use a form of trial and error learning that strengthens with every attempt. Despite their rapid movements, flies pause often enough to process outcomes where food was found, which escape angles worked best, or which surfaces felt safest to land on. Their brains contain neural circuits that increase responsiveness to successful behaviors, allowing them to refine flight paths and timing. When trained in laboratory settings, flies quickly learn to associate patterns of light or scent with rewards, showing that even brief experiences create measurable changes in their nervous systems. In natural settings, repeated exposure to the same terrain teaches them how to navigate air currents and avoid obstacles with increasing confidence. Their learning feels almost rhythmic, shaped by the beat of their wings. And with each lesson absorbed, the deeper intelligence of insect life continues unfolding. Crickets, recalling successful shelters, rely on a simple but effective form of spatial memory. After exploring an area at night, they remember which hiding spots provided warmth, stillness, and protection. Their antennae scan surfaces for familiar textures, while their legs sense subtle temperature differences that hint at safety. Even small details, a curved leaf, a patch of soft soil, the shadow of a stone become memory anchors that guide them back when danger approaches. Experiments show crickets return with surprising consistency to shelters that kept them safe before, avoiding spaces where they felt exposed. Their decisions unfold quietly, shaped by repeated moments of comfort. And as crickets slip back into trusted hideaways, paper wasps nearby engage in their own remarkable form of memory, recognizing friends within their colony. Paper wasps remembering friends demonstrate a level of individual recognition rare among insects. They identify specific colony members by the unique patterns on their faces, storing these markings in specialized areas of the brain devoted to visual processing. When two wasps meet, brief antennal touches confirm identity, reducing conflict and reinforcing social structure. This ability allows colonies to maintain order, ensuring that familiar workers cooperate more smoothly, while unfamiliar wasps are treated cautiously. Recognition persists over time, enabling stable relationships even as tasks change throughout the season. The soft buzz within a paper wasp nest is more than random movement. It is a network of individuals who truly know one another. And while wasps use faces to navigate their social world, termites rely on spatial memory to maintain the shapes of their intricate underground tunnels. Termites, memorizing tunnel shapes, use a blend of chemical cues and physical familiarity to navigate their dark networks. Although they cannot see, the contours of each passage, its width, slope, and branching angles become part of an internal template formed through repetition. As termites travel, their bodies brush against tunnel walls, reinforcing a tactile memory that guides them back to key chambers. If part of the network collapses or shifts, termites explore gently until they reconstruct a familiar pattern, using pheromones to mark new paths. Their collective memory ensures that airflow, humidity, and temperature remain balanced throughout the colony. These underground architects maintain stability through constant soft adjustments, and above them, butterflies drift through sunlight, recalling nectar sources with delicate precision. Butterflies recalling nectar sources rely on visual, chemical, and spatial memory to revisit flowers that once offered rich rewards. Their compound eyes recognize colors and patterns from a distance, while their legs taste a flower the instant they land on it. After a successful feeding, neural circuits store the scent and visual signature of that blossom, guiding the butterfly back even hours later. They also remember the timing of blooming cycles, returning to patches that refill nectar at predictable intervals. During migration, this memory becomes essential, helping them conserve energy by choosing only the most promising flowers along the way. And as butterflies follow these remembered trails of sweetness, insects across ecosystems practice quiet problem-solving through the interplay of instinct and experience. Insects practicing quiet problem-solving blend inherited behaviors with small adjustments learned through daily life. Whether choosing shelters, navigating obstacles, or locating food, they refine their strategies through repetition and subtle feedback from their environment. Simple neural loops compare past outcomes with present conditions, allowing insects to tweak movements, shift priorities, or abandon failing attempts. This type of problem-solving appears in ants selecting shorter routes, bees optimizing foraging patterns, beetles testing different hiding spots, and even larvae adjusting their feeding rhythms. Their decisions emerge silently, shaped by micro-memories stored throughout their bodies and brains. Though tiny, these choices accumulate into behaviors that appear almost deliberate. And with each quiet solution, the hidden intelligence of insect life becomes more visible. To survive such small worlds, insects rely on senses tuned to the faintest signals. Antennae detecting tiny temperature shifts act like exquisitely sensitive thermometers, constantly monitoring the heat around an insect's body. These antennae contain specialized cells that respond to variations as small as a fraction of a degree, helping insects choose paths that support their delicate metabolism. A slightly warmer breeze may indicate sunlit shelter. A cooler pocket might warn of predators hiding in shade. By reading these thermal gradients, insects conserve energy and avoid stress. Antennae sweep gently through the air, gathering a layered picture of warmth that guides flight, foraging, and rest. And while these subtle temperature readings shape their daily rhythms, eyes above them sense polarized sky patterns that help insects move with steady confidence. Eyes sensing polarized sky patterns give insects a way to navigate even when the sun is hidden behind clouds or horizon. Compound eyes contain photoreceptors that detect the direction in which sunlight scatters across the atmosphere, forming invisible bands of polarization. Bees, ants, and some beetles use these patterns as a compass, aligning their movements with the sky's soft geometry. The patterns shift as the day progresses, offering insects a reliable cue even during twilight. In open fields, polarized light helps them fly straight despite crosswinds. In forests, it guides them through drifting beams that slip between branches. This skyborne information blends with terrain cues to create a stable sense of direction. And beneath these guiding patterns, insects also feel the ground's faint tremors through the sensitive receptors in their legs. Legs feeling subtle ground tremors allow insects to hear vibrations traveling through soil, wood, or leaf litter. These tremors carry information about approaching footsteps, shifting weather, or other insects moving nearby. Tiny mechanoreceptors on the legs bend in response to the slightest pulse, triggering neural signals that help insects interpret distance and threat. Caterpillars freeze when they detect the tremor of a bird landing on a branch. Ants adjust foraging routes based on the vibrations of other colonies tunneling in the earth. Even soft breezes, shaking grass send patterns through the ground that insects use as environmental cues. This tactile awareness helps them stay hidden and choose safe paths. And as vibrations guide their movements, their wings adjust to micropressure changes in the air around them. Wings adjusting to micropressure enable insects to fly with extraordinary stability despite unpredictable air currents. Each wing contains veins and sensory cells that detect minute shifts in airflow eddies from leaves, thermal rises from sunlit rocks, or sudden dips of cool air at dusk. In response, insects tilt their wings by tiny angles, compensating instantly to maintain smooth flight. Dragonflies adjust each wing independently, while butterflies balance lift with slow, wide strokes. Even beetles, with heavier bodies, use micropressure feedback to avoid collisions and conserve energy. These adjustments create graceful, floating movements that seem effortless. And once they land, another set of senses becomes active mouthparts that taste minerals in dew resting on leaves. Mouthparts, tasting minerals in dew, help insects assess the nutritional quality of their surroundings. Dew droplets collect trace elements from soil, plant surfaces, and the air, forming tiny reservoirs of information. When insects touch these droplets with their mouthparts or feet, specialized chemoreceptors detect salts, sugars, and organic compounds. These signals help them decide whether a plant is healthy, whether territory is suitable, or whether another feeding spot is needed. Early morning dew also provides hydration, essential for insects that lose water quickly through their exoskeleton. As they sip, the cool moisture steadies their internal balance, preparing them for the day's movements. And with each delicate taste, more subtle layers of sensory wisdom unfold. Feet sensing plant chemistry allow insects to evaluate their environment the instant they touch down. Many species have chemoreceptors on their tarsi, tiny sensory cells that taste the surface beneath them. When a butterfly lands on a leaf, its feet detect sugars, toxins, moisture, and even the plant's stress signals within moments. These chemical impressions help insects decide whether the leaf is suitable for feeding, egg-laying, or resting. Ants use this same sensitivity to distinguish between friendly plants and those releasing defensive compounds. Beetles feel chemical gradients that guide them toward decaying wood with optimal nutrient levels. Each step becomes a quiet dialogue between insect and plant, shaping movement through subtle, invisible cues. And just as insects taste their surroundings through their feet, they also read humidity layers using the soft sensors in their abdomens. abdomens reading humidity layers help insects maintain their delicate water balance. Their bodies lose moisture quickly, so detecting shifts in humidity is essential for survival. Specialized hygroreceptors, tiny cells responsive to water vapor, line the abdomen and antennae, allowing insects to sense differences in air moisture as they move between shaded leaves, open sunlight, or underground tunnels. A slightly damp breeze may guide them toward shelter, while a dry current warns them to conserve water. Mosquitoes use humidity gradients to locate warm-blooded hosts. Ants rely on them to choose nesting sites. Even small nocturnal insects navigate by these invisible layers, drifting toward microclimates that protect their fragile bodies. And as humidity shapes their quiet choices, whisker-like hairs come into play, decoding the movement of air with exquisite precision. Whisker-like hairs decoding airflow act as ultra-sensitive motion detectors on an insect's body. Known as trichoid sensilla, these hairs bend when air currents pass over them, sending immediate signals to the nervous system. This allows insects to detect predators approaching from behind, avoid collisions during flight, or align themselves with favorable breezes. Dragonflies use these hairs to sense the slipstream around their wings, adjusting position mid-flight with near-instant accuracy. Ground insects feel the whisper of wind through grass, using it to predict weather shifts or locate hidden openings between leaves. These airflow cues exist at a scale too small for humans to perceive, yet they shape how insects move through their world. And while airflow guides them, some insects hear through their body walls, sensing vibrations in an entirely different way. Insects hearing through body walls interpret sound vibrations without traditional ears. Many species have tympanal organs, thin, drum-like membranes embedded in their thorax, abdomen, or legs. These membranes vibrate when struck by sound waves, allowing insects to detect frequencies far beyond human hearing. Katydids can sense ultrasonic calls from bats. Moths hear approaching predators before they appear. Some ground insects even perceive sound through their exoskeleton, feeling low-frequency vibrations that travel through soil or wood. This ability helps them communicate, avoid threats, and respond to subtle environmental changes. The soundscape becomes a tapestry of pulses and tremors woven through the air and earth. And when vision fails completely, another ability emerges, a kind of sixth sense orientation used in total darkness. Sixth sense orientation in total darkness arises from the integration of multiple subtle cues: magnetic fields, airflow, humidity gradients, and chemical traces. Insects with limited or no eyesight navigate confidently through nighttime forests, underground tunnels, and shadowed leaf litter by relying on these combined signals. Some species detect Earth's magnetic field through specialized proteins. Others use memory of temperature pockets or scent gradients to stay oriented. Even the pattern of air movement between obstacles helps them build mental maps of their surroundings. This quiet, multisensory blend functions like an inner compass, guiding them without sight. And with each step made in darkness, we see how deeply intertwined perception and intelligence are within the insect world. Even survival, in the insect world, is practiced through subtlety, not force. Leaf insects, choosing gentle hiding spots, rely on extraordinary camouflage, blending seamlessly with the foliage around them. Their bodies mimic leaf veins, edges, and even tiny imperfections like bite marks or browning patches. When selecting a resting place, they evaluate leaf color, light angle, and ambient motion to ensure their disguise remains convincing. Their legs test the stability of stems, while their antennae sense airflow to predict whether the breeze will sway them naturally with the plant. If danger approaches, they often freeze completely, allowing their silhouette to dissolve into surrounding greenery. Some species even rock gently, mimicking leaves caught in wind. This silent strategy keeps them hidden without conflict. And while leaf insects hide through mimicry, ants nearby protect their colonies by relocating nurseries before storms arrive. Ants relocating nurseries before storms demonstrate a remarkable ability to forecast weather through sensory cues. Drops in barometric pressure, rising humidity, and changes in wind patterns alert them that heavy rain is near. Workers quickly gather larvae and pupae, carrying them into deeper chambers where flooding is less likely. They reinforce tunnels, seal small entrances with soil pellets, and adjust ventilation pathways to maintain safe humidity levels underground. Each movement is purposeful yet calm, guided by instinct refined over millions of years. Colonies that survive seasonal storms do so thanks to this collective foresight. Even after the worst rainfall, ants reopen blocked passages and rebuild outer chambers with quiet efficiency. And while ants anticipate storms, beetles adopt a different form of subtle defense, faking stillness to survive. Beetles faking stillness to survive use a strategy called tonic immobility, entering a temporary state that mimics death when threatened. Their muscles lock gently, bodies relax, and legs curl inward, making them appear lifeless to predators that prefer moving prey. This behavior is triggered by pressure changes, sudden shadows, or vibrations in the ground. During stillness, beetles reduce metabolic activity, conserving energy and lowering their scent profile. Some species even release faint chemicals that mimic decay, strengthening the illusion. When danger passes, they awaken gradually, sensing the environment with antennae before resuming movement. This quiet act of self-preservation requires no aggression, just patience and subtle timing. And while beetles survive through stillness, butterflies practice their own gentle strategy by seeking safe microclimates throughout the landscape. Butterflies, selecting safe microclimates, choose resting spots based on temperature, wind, and light, all essential for regulating their delicate bodies. Their wings absorb warm sunlight, helping them maintain the energy needed for flight, while shaded areas offer refuge from excessive heat. By testing air currents with small wing beats, they detect places where the breeze remains soft and steady. Moisture levels also influence their choices. Some butterflies settle near dew-rich vegetation that keeps their bodies hydrated. During storms, they cling to the underside of leaves, using the leaf's curve as a natural shield. Even slight changes in color or texture beneath them shape their decisions. And while butterflies seek balance in the open world, bees adjust their hive environment from within, maintaining temperature with remarkable precision. Bees adjusting hive temperature perform one of the most sophisticated climate control behaviors found in insects. When the hive becomes too warm, workers fan their wings in coordinated rhythms, creating gentle airflow that cools the brood chamber. If the hive grows too cold, bees cluster tightly together, vibrating their flight muscles to generate heat without taking off. These coordinated actions keep the internal temperature stable, often within just 1 degree, ensuring larvae develop properly. Bees also regulate humidity by collecting water droplets and spreading them along the comb to promote evaporation. Each adjustment is small, yet collectively, the hive becomes a self-regulating structure. This subtle climate engineering allows bees to thrive in environments that swing between extreme temperatures. And with each cooling fan and warming vibration, insects demonstrate how survival can unfold softly, without force. Aphids, signaling silent danger, rely on a delicate form of chemical communication. When a predator disturbs the plant they feed on, stressed individuals release alarm pheromones, tiny molecules that drift through the air in soft, invisible pulses. Nearby aphids sense these cues instantly through receptors on their antennae, prompting them to freeze, drop from leaves, or cluster tightly for protection. The signal is faint and dissipates quickly so the group doesn't panic unnecessarily, but strong enough to ripple across a colony in moments. Plants themselves often respond by altering their sap chemistry, providing additional hints of danger. Even small shifts in humidity and vibration reinforce the message. And once the danger eases, the air clears, allowing aphids to resume their gentle feeding. As their alarm fades, Dragonflies nearby choose calm escape routes with an elegance shaped by wind, brightness, and instinct. Dragonflies choosing calm escape routes rely on a combination of predictive vision and sensory feedback to slip away from threats with minimal effort. Their compound eyes track approaching motion in panoramic detail, allowing them to estimate danger long before it reaches them. Instead of darting randomly, dragonflies chart smooth escape lines shaped by airflow, sunlight angles, and the positions of surrounding vegetation. Their wings adjust microseconds ahead of turbulence, letting them glide into open patches of air that offer the least resistance. These escape routes often curve gracefully through reeds or above still water, blending speed with control. Even when startled, dragonflies rarely collide with obstacles. They choose paths that maximize space and minimize energy use. And while they navigate open skies, wasps nearby take a slower, more architectural approach by optimizing the positions of their nests. Wasps, optimizing nest positions, consider warmth, shelter, airflow, and safety before committing to a building site. Scouts inspect potential locations under eaves, within shrubs, inside hollow stems, judging each one through repeated landings and brief antennal touches. They assess temperature stability by sensing how surfaces absorb sunlight during the day and release it at dusk. Airflow matters too. Wasps avoid areas where wind disrupts communication or cooling behavior. Even subtle vibrations from predators influence their choices. Once a location feels right, the first layers of the nest anchor into place, and workers reinforce the structure with paper-like material made from chewed fibers. If conditions shift unexpectedly, wasps may strengthen walls or adjust the nest's orientation. And beneath these aerial architects, termites seal their tunnels with precision, shaped by equally delicate environmental cues. Termites, sealing tunnels with precision, respond instantly to changes in humidity, vibration, and airflow inside their underground chambers. When a breach occurs, whether from predators, collapsing soil, or shifting roots, workers gather soil pellets, saliva, and plant fibers to patch the opening. Each repair action is small, but thousands of coordinated movements restore structural stability in minutes. Termites sense the exact width needed to maintain ventilation, narrowing or widening tunnels to keep temperature and moisture levels optimal for the colony. Their antennae sweep the edges of the damage, reading texture and moisture to adjust material choice. Once the repair dries, it blends seamlessly into the existing architecture. And while termites seal their hidden worlds, other insects practice mimicry above ground, using quiet illusion as a survival tool. Insects using mimicry with quiet intention rely on patterns, colors, and shapes that dissolve them into their surroundings. Leafhoppers imitate veins and stems. Walking sticks become slender twigs. Some moths mirror tree bark so precisely that even close inspection cannot reveal their outline. This mimicry isn't conscious choice, but behavior and positioning play a crucial role. Many insects adjust posture, orientation, or movement to enhance the illusion. A slight tilt aligns them with leaf grain. A slow sway mimics wind. Stillness completes the effect. Predators scanning the environment overlook them as part of the scenery. Some species even mimic dangerous insects, adopting warning colors or false eye spots that deter attacks. In these soft acts of deception, survival unfolds without confrontation, only patience and stillness. Pollinators synchronizing with seasons help entire ecosystems move in a steady, reliable rhythm. Bees, butterflies, moths, and hoverflies emerge when temperature, daylight, and floral chemistry reach the exact balance they need. Their internal clocks respond to subtle cues, lengthening mornings, gentle warming of soil, the scent of new nectar rising with spring air. As flowers open in staggered waves, pollinators match those timelines almost perfectly, ensuring each bloom receives attention in its brief window. Their movements are quiet, rhythmic, and essential, transferring pollen in soft brushes of wing and leg. When a season arrives early or late, pollinators adjust their emergence by sensing humidity shifts, light gradients, and plant signals. These tiny synchronies shape entire landscapes, supporting fruit, seeds, and new growth. And as they move between blossoms, ants below contribute to the same harmony by aerating soil gently. Ants aerating soil gently shape ecosystems from beneath the surface. Their tunnels allow air, moisture, and nutrients to move more freely through packed earth, creating microchannels that plants depend on. As ants dig, they redistribute minerals and organic matter, mixing layers that would otherwise remain static. This quiet engineering improves root growth, drainage, and overall soil health. Ants also bring seeds underground, where some germinate safely in nutrient-rich chambers. Their waste enriches the soil, adding nitrogen and essential microbes. Because colonies expand gradually, their impact feels soft, yet steady, improving the land over seasons and years. And while ants loosen and enrich the ground, beetles above continue the cycle of balance by recycling fallen wood into new life. Beetles recycling fallen wood play a key role in returning nutrients to the ecosystem. Bark beetles, wood borers, and decomposer species tunnel through dead branches and logs, breaking fibers into smaller pieces that fungi and microbes can finish converting. Their mouthparts scrape fibers gently, creating fine channels that increase airflow and moisture inside the wood. This accelerates decay in a steady, natural rhythm. Many beetles carry fungal spores on their bodies, introducing them into fresh wood and starting decomposition earlier. As logs crumble, nutrients return to the soil, feeding mosses, seedlings, and surrounding plants. Even abandoned beetle burrows become microhabitats for spiders, springtails, and small larvae. With each quiet excavation, wood becomes soil again. Meanwhile, in the driest regions, termites support this same balance by enriching landscapes that receive almost no rain. Termites enriching dry landscapes turn harsh, arid environments into places where life can take hold. Their mounds collect moisture, moderate temperature, and concentrate minerals that nearby plants depend on. Termites break down tough plant material that few other creatures can digest, converting dry grass and wood into nutrient-rich soil. Their tunnels improve water infiltration during rare rains, allowing vegetation to root more deeply. Entire patches of green often form around termite mounds, creating islands of fertility across savannas and deserts. These nutrient hubs attract grazing animals, insects, and birds, forming miniature ecosystems built on termite engineering. Even in drought, termites maintain internal humidity with carefully sealed chambers and soil mixtures. As they shape dry worlds into livable ones, fireflies contribute a different kind of harmony, one that glows softly through the night. Fireflies, shaping night rhythms, do so through gentle pulses of bioluminescence, creating patterns that drift across summer darkness like drifting constellations. Each species flashes at its own tempo, forming light rhythms that help individuals find mates without confusion. These flashes respond to temperature, humidity, and even moonlight, shifting subtly as the night changes. Fireflies also coordinate their patterns in groups, producing synchronized waves of light that roll across fields and riversides. Their glow supports nighttime ecosystems by attracting tiny insects that use the light as orientation cues, while predators learn to avoid fireflies due to their chemical defenses. The result is a calm choreography of signal and response, a luminous language woven into the landscape. And from this glowing rhythm, the final set of ecosystem intelligences emerges, completing the balance insects create. Butterflies choosing migration timing rely on a combination of internal clocks, temperature cues, and subtle environmental signals. Their bodies sense day length with remarkable accuracy, allowing them to detect when seasons begin shifting, even before weather changes become obvious. As light hours shorten or lengthen, hormonal shifts prepare them for long journeys. They test air currents with gentle wing beats, reading humidity, temperature gradients, and wind direction to decide when conditions are calm enough to begin traveling. Some species rely on stored magnetic information, orienting themselves along routes their ancestors used for generations. Others follow the scent of flowering plants carried across distances by warm breezes. These migrations unfold like drifting ribbons across continents, quiet but precise. And while butterflies move across wide landscapes, predatory insects below maintain balance through their own subtle, stabilizing behaviors. Predatory insects controlling calm balance help keep ecosystems from tipping into chaos. Lady beetles, lacewings, dragonfly nymphs, and praying mantises all regulate herbivore populations with targeted, efficient hunting. They listen for faint leaf vibrations, track chemical trails left by prey, and use quick bursts of movement to maintain the equilibrium of their surroundings. Their feeding prevents plant overconsumption, allowing grasses, shrubs, and trees to maintain steady growth. Even aquatic predators like water beetles and damselfly larvae contribute to balance within ponds and streams, ensuring algae and small invertebrates don't overwhelm quiet habitats. These predators rarely cause disruption. Instead, they move with careful timing, taking only what they need. And while they protect vegetation indirectly, ants take a more direct role by guiding plant growth through their soil-shaping behavior. Ant colonies guiding plant growth influence ecosystems in ways that feel soft and almost invisible. Their tunnels circulate oxygen through compacted earth, allowing roots to penetrate deeper. As ants transport seeds, intentionally or incidentally, they bury them in nutrient-rich chambers that encourage germination. Some seeds even rely on ants entirely, offering tiny food rewards in exchange for safe dispersal. When ants deposit their organic waste into the soil, they enrich it with nitrogen and beneficial microbes, strengthening plant health over time. Colonies relocate materials in patterns that subtly shift how water flows after rainfall, creating microlandscapes that shape plant distribution. The result is quiet but profound, and while ants influence soil and seed, bees continue the process above ground, tuning pollination routes with remarkable precision. Bees tuning pollination routes optimize their foraging patterns through memory, scent mapping, and communication. Each bee remembers the angles of sunlight that reach specific flowers, the time of day when blooms open, and the scent markers left by earlier visitors. As they revisit flowers, they adjust their paths to minimize energy use, creating stable loops known as traplines. These routes help flowers receive consistent pollination, supporting fruit and seed development across entire fields. When conditions shift cloud cover, wind speed, or floral abundance, bees revise their loops, sharing new information through soft movements inside the hive. Their collective adjustments shape the productivity of whole landscapes. And as bees refine these routes, countless other insects play supporting roles that maintain the quiet harmony of ecosystems everywhere. Insects supporting quiet ecosystems do so through thousands of small, interconnected tasks that remain almost invisible to the human eye. They pollinate plants, recycle nutrients, clean decay, aerate soil, disperse seeds, and maintain food webs with unbroken consistency. Each species contributes a different thread to the ecological fabric, some through flight, some through burrowing, others through the simple act of feeding. Their presence ensures that forests regenerate, wetlands filter water, grasslands thrive, and even deserts sustain pockets of life. Many insects also provide food for birds, mammals, reptiles, and amphibians, linking every level of the ecosystem. Their collective intelligence emerges not from noise or force, but from steady, synchronized behavior. Through this calm cooperation, entire habitats stay balanced and alive. Microbrains working with perfect efficiency show how insects achieve clarity without complexity. Their neural circuits are compact, streamlined, and specialized, allowing fast decisions using minimal energy. Instead of thinking in the human sense, Insects process the world through finely tuned pathways sensing light, vibration, chemistry, and humidity with remarkable precision. Each neuron contributes purposefully, forming loops that guide movement, feeding, navigation, and communication. This efficiency creates a form of intelligence shaped not by size but by elegance. Every action unfolds with quiet accuracy, from landing on a swaying leaf to adjusting wings for gentle wind. These tiny brains create fluid coordination within the individual insect, which becomes even more extraordinary when multiplied across a colony. And as single minds work efficiently, hive minds emerge like soft rivers moving together. Hive minds flowing like soft rivers form when thousands of insects synchronize their actions without a leader. Each insect follows simple rules, respond to scent, airflow, temperature, vibration, and yet the group behaves as a unified organism. Within a beehive, temperature stays stable because individuals align their movements. Within an ant nest, tunnels expand because workers adjust to each other's pace. Termites build towering structures without blueprints, guided only by tiny chemical cues exchanged between individuals. These coordinated behaviors resemble currents in a river, each insect acting like a droplet, contributing to a greater flow. This collective intelligence solves problems too large for any single member, maintaining balance with elegant subtlety. And as colonies move in these gentle rhythms, individual wing beats rise and fall in harmony with sunlight. Wing beats syncing with sunlight create a natural rhythm that guides daily insect life. Many species time their activity to the angle, warmth, and color of incoming light. Bees begin foraging when sunlight reaches a certain intensity. Butterflies warm their wings before taking flight. Dragonflies hover where sunbeams create calm thermal pockets. Even the sound of wings changes slightly with temperature, forming soft pulsations shaped by the day. These wing beats help insects regulate energy, avoid predators, and find food, all while following the quiet pulse of the sky. Light becomes a partner rather than a force guiding movement, timing, rest, and shaping behavior. As wings respond to sunlight, senses tune themselves to the faintest signals Earth provides. Senses tuning to Earth's faint signals allow insects to perceive details far beyond human awareness. Their antennae read chemical trails left hours before. Their legs detect vibrations from distant footsteps. Their eyes follow polarized patterns invisible to most animals. Some species feel subtle shifts in humidity that precede rainstorms. Others sense magnetic fields to navigate through darkness or across long distances. These signals may seem quiet or insignificant, but insects weave them into precise maps of their surroundings. Even in complete darkness, they remain oriented through combinations of airflow, temperature, and pressure. Their perception forms a soft, yet complete understanding of the environment. And as these senses shape daily choices, memories drift through entire colonies like shared whispers. Memories drifting through whole colonies reflect the collective learning that insects pass between individuals. When a bee discovers a rich patch of flowers, the information spreads through dances and scent trails. When ants find a safe route, pheromones preserve it for days. Entire groups learn which plants bloom earliest, which shelters stay dry, and which pathways remain free of predators. These memories persist not in a single insect, but in the colony's shared patterns, shaping behavior through seasons. Young workers inherit the wisdom of older ones simply by following established cues. The result is a calm continuity, where learning flows softly through generations. And within this unbroken transmission, the deep calm of insect life becomes unmistakable. Hidden wisdom in gentle choices appears in the way insects respond to tiny environmental shifts. Their decisions, where to land, when to move, which direction to turn, are guided by microsignals that humans rarely notice. A slight vibration may tell a beetle to pause. A faint scent may guide an ant toward food. A small rise in humidity may convince a moth to take shelter. These choices accumulate into patterns that sustain survival without noise or force. They reveal an intelligence shaped by precision, not deliberation. This subtle wisdom passes through forests, grasslands, and fields as insects interact with the plants and soil around them. And as these decisions ripple outward, soft intelligence begins shaping quiet forests themselves. Soft intelligence shaping quiet forests comes from the countless interactions insects have with vegetation. Pollinators maintain flowering cycles, decomposers return nutrients to the soil, and burrowing insects open pathways for air and water. Even pests, in small balanced numbers, help plants strengthen their defenses. Trees rely on insects to distribute pollen, recycle fallen wood, and control leaf growth. Through these gentle, continuous actions, forests remain resilient, able to grow, regenerate, and adapt. The calm hum beneath the canopy is not random. It is a coordinated network built on insect behaviors. Their presence guides which seedlings survive, how soil breathes, and where nutrients settle. And when the sun sets, this intelligence continues through insects that read the night sky in their own quiet way. Night insects reading starlight navigate through a world where light is faint and scattered. Many species use celestial cues, patterns of stars, the arc of the Milky Way, and the polarization of moonlight to orient themselves across open landscapes. Their compound eyes amplify dim light, allowing them to detect movement and direction where most animals see only darkness. Some moths fly by maintaining a constant angle to the moon, while others use gradients of night brightness to stay aligned. Even fireflies respond to the intensity of starlight when timing their flashes. These nighttime behaviors maintain the rhythm of nocturnal ecosystems, and when morning arrives, day insects take over, following warming winds that guide their gentle movements. Day insects, following warming winds, respond to temperature gradients that rise from sunlit ground. Butterflies open their wings to absorb heat, then ride soft thermals to conserve energy. Bees gauge wind direction when planning foraging routes, choosing paths where breezes help carry their scent trails. Dragonflies hover in pockets of warm air, using them like invisible platforms. These warming winds shape daily schedules: when to feed, when to rest, when to return home. Even slight changes in temperature can signal seasonal shifts, helping insects adjust to emerging flowers or approaching storms. The world becomes a map drawn by warmth, scent, and pressure. As insects follow these subtle paths, the final truth of their world becomes clear. A quiet thinking woven through all insect life. The quiet thinking woven through all insect life is not thought in the human sense, but a tapestry of coordinated instincts, sensory wisdom, and tiny decisions that hold ecosystems together. Each insect contributes a thread: the pollinator choosing a flower, the ant opening a tunnel, the beetle recycling fallen wood, the moth navigating by moonlight. Together, these threads create balance across forests, fields, wetlands, and deserts. Their intelligence emerges through harmony rather than hierarchy. Every action small, every contribution essential. Even the silence of their movements reflects an ancient rhythm that predates human history. Insects show that life does not need noise to be complex, nor consciousness to be profound. Their quiet intelligence sustains the world gently, patiently, continuously. As we come to the end of these 100 quiet facts, you may notice something subtle, something that has been unfolding beneath the surface the whole time. In learning about insects, we often expect speed, activity, or noise. But here, in this slow and gentle space, what emerges instead is stillness, a deeper rhythm, a way of existing in the world that depends not on size or strength, but on noticing. Insects survive by paying attention to what many other creatures overlook: the shift of a breeze, the softness of a shadow, the faint change in humidity layered through the air. They navigate entire landscapes using cues so delicate that humans rarely feel them at all. And although their minds are small and their lives are brief, they shape the balance of ecosystems with remarkable consistency. Every forest, every field, every patch of wild grass relies on thousands of these quiet decisions when a bee chooses one flower over another, when an ant redirects a tunnel, when a beetle begins breaking down a fallen branch. These tiny choices accumulate into something vast. They create harmony without being aware of it. They keep soil rich, water clean, plants pollinated, and food webs connected. The world is held together not only by the large and powerful, but by the small and unnoticed. And perhaps there is a kind of comfort in that, a reminder that gentleness is not weakness, and that quiet effort can shape entire landscapes. As you settle further into rest, think of the way insects move through their world, how their wings catch light as softly as dust drifting in a sunbeam, how their footsteps barely disturb the surface of a leaf, how their communication travels as faint scents and vibrations rather than words. Everything they do is guided by calm efficiency, a kind of intelligence that asks for no recognition, no noise, no celebration, just presence and precision, just existing in tune with their surroundings. Maybe your day was full of tasks, decisions, and noise. Maybe your mind feels cluttered, or stretched, or tired. Here, you don't need to hold anything. You don't need to match the pace of the day or solve anything that felt tangled or heavy. You can simply drift the way a butterfly drifts on a warm current. You can settle the way a moth settles on a quiet surface. You can let your thoughts soften like a field of grass moving in a gentle breeze. Insects remind us that intelligence doesn't always look like thinking. Sometimes it looks like adapting. Sometimes it looks like listening. Sometimes it looks like choosing the calm path instead of the frantic one. And sometimes it looks like letting the world carry you just a little, instead of holding everything yourself. If your eyes feel heavier, let them close. If your breath feels slower, let it stay slow. Imagine a meadow humming softly at the edge of day. Tiny wings shimmer in low light. Air moves through tall grass in long, quiet waves. Every small creature knows exactly where it belongs, exactly what it needs, without rushing or forcing anything. In that world, nothing is hurried, nothing is loud, nothing is expected of you. If this video helped you rest, you're welcome to subscribe whenever you wake. It helps others find a place where they can slow down too. For now, let the hum of insect life fade into the background of your breathing. Let the calm rhythm of small minds guide you toward rest. May you drift easily. May your mind quiet gently, and may sleep come to you the way wings flutter through warm air, light, soft and unhurried. Good night.